Welcome to Lecture 4, Carnegie Mellon 21499. We're going to talk about Benford's law of digit bias. So this is a fascinating topic. There are a lot of different ways to attack the problems. Depending on what your background is, there's a whole slew of things you can be looking at. All right. So here is a motivating question. Say you have some set of data. Maybe it's stock prices, street addresses, telephone numbers, and you want to know Fibonacci numbers, how often is the first digit of 1? Well, if it's something nice like the Fibonacci numbers, you can just start enumerating them and just count. And so if you get bored later today, just start writing Fibonacci numbers. Do not give me correct answers. Just what's your first instinct for how often you should have a first digit of 1? What's the first thing you should say? Don't worry about being correct. What should your gut tell you? 10 or 11%. So the first thing is maybe 10%, and then you correct to 11% because you're not going to see 0 as a first digit. If it's 0.0013, you'd write that as 1.3 times 10 to the negative. So, 1/10, 1/11. And so you might expect some kind of fluctuations like this. It turns out that in a lot of systems of data, you have about 30% of the time starting off with a 1, and only about 4.6% of the time starting off with a 9. In addition to being of interest, this is actually has a lot of fascinating applications. So if you look at Fibonacci numbers fit this very well. I would prefer not to mention how I got the stuff for the second plot. Twitter uses by followers, distances of stars from Earth. And different things will have a better fit to Benford than others, and the general rule is the more things you amalgamate and average over, the better fit in general you will get. So I want to explain Benford's law, give some examples, sketch some proofs, and talk a little bit about some open problems. So the first thing is, I've mentioned this has applications. The IRS loves this because you can use it to detect tax fraud. And in fact, years ago, I got an email which began, greetings, my name is blah, blah, blah. I'm a senior criminal investigator at the Internal Revenue Service. And it was a couple of minutes before I could read the rest of the email, which continues, I read with great interest your recent paper in Acta Arithmetica. And I was such a newly minted PhD that I was just thrilled that somebody was reading it. It's like, yeah, yes, because the IRS cares about detecting tax fraud. And when you only have finite resources, you want to use them in the most productive ways. So which companies are more likely than not to be committing fraud based on numbers? So just because, however, a test says something suspicious might be happening, that is not the same as proving that something suspicious has happened. So we did an XKCD, I will do a Dilbert. I did email Scott Adams, and he was kind enough to allow me to reproduce this. Your travel expenses are rejected because all of your meal costs are round numbers. You're a liar or worse. I decided what to order based on what totals to a round number after 50% tip. That's worse. So you do have to be careful about what are the explanations behind the behavior. So there are a lot of different systems where you will see Benford's law. And some of the ones that are really important, products of random variables, differences of order statistics, recurrence relations, which are like discrete versions of differential equations. These things model so many things in the real world that if these are Benford, you'd expect a lot of other things to be Benford as well. So some of the applications is determining, round-off errors in computer science, optimal ways to store numbers, detecting tax and image fraud. And this is what the IRS and other people love, and we'll talk a little bit more about that later. So some general theory. So I've mentioned for many data sets, the probability of having a first digit base B of D is D plus 1 over D. As a nice exercise, you show that all these, if you sum them, will sum up to 1, so it is a probability distribution. All right. So just some background material. We say A is equal to B mod C if A minus B is an integer times C. So 17 is 5 mod 12. Everybody's familiar with clock arithmetic. That's essentially what this is. If it's 10 o'clock, what time is it in 5 hours? It's 3. So we're saying 10 plus 5 equals 3. The next is notation. So if we have a number, we can write a number x as a significand times 10 to a power. We'll assume x is a positive number here. If it was a complex number, you would have a phase, and then you would be writing the absolute value like this. And two numbers have the same significand if and only if they have the same leading digits. So if I want to understand leading digits, it's enough to understand the significand, because that's just getting rid of those paddings of zeros. And the key observation is the log of x base 10 is equal to the log of x tilde base 10 mod 1, if and only if they have the same leading digits. Because if they differ, they'll differ by 10 to the k. And when you take the log of 10 to the k base 10, that's just k. And since we're looking at things mod 1, that k is going to disappear. And this gives you an idea of why Fourier analysis is going to be useful. If I have e to the 2 pi iu, has everybody seen this notation, e to the 2 pi iu? Okay, so exponent of 2, I'll do ix is cosine x plus I sine x. This is the great Euler formula, or sometimes Euler codes. So you can prove all of trigonometry very quickly from this. So if people are interested, after we break, I'll show you how to derive all of trigonometry from essentially this relation. If you increase x by 2 pi, you return to where you started. So when we look over here, if I look at 2 pi iu, or if I look at 2 pi I times u mod 1, I can't tell the difference. In general, if you chop off, it's like Queen of Hearts and Alice in Wonderland. If you chop off the integer part of a number and then put that in a function, that's different than if you put in your number to the function. Normally the integer part is important. Well, what this is saying here is that if we're doing exponentials, I can throw away the integer part of u and nothing is going to hurt me. And that shows you why Fourier analysis is going to be so useful for studying so many problems in Benford's law. If you've heard of the Mellin transform and the Fourier transform are essentially the same. They differ by a logarithmic change of variables. It's just how you want to write things. And not surprisingly, there's going to be a lot of logs going on. And so this advice of taking logarithms is really going to come into play. All right, concept of equidistribution. We say a sequence is equidistributed mod 1 if the probability that we land in an interval AB tends to be minus A. So AB is just some subinterval of 0, 1. So the fraction of the time we're in the interval just goes to its measure. So in the interval 1/3 to 2/3, 1/3 of the time in the limit. And so here's a nice theorem. If beta is irrational, then n beta is equidistributed mod 1. There's a lot of nice proofs of that. What if beta were not irrational? What if beta was 1/5? Do you think the fractional parts of n over 5 could be equidistributed? Well, you'll get 0, 1/5, 2/5, 3/5, 4/5, and then 5/5 is just 0 again. 6/5 is the same as 1/5. 7/5 is the same as 2/5. So if beta is rational, this is going to just cycle through the same values again and again. So it clearly can't be equidistributed if beta is rational. What's nice is that if beta is irrational, it will be equidistributed. And for some problems, the rate of convergence to equidistribution will depend on how irrational or the irrationality type of beta. And we will get to use, at some point, the largest finite number I have ever used in any of my math proofs. All right, so this is going to be one of our main tools for proving Benfordness, if we're lucky enough to be in a situation like this. The log of 2 base 10 and the log of the golden mean are both irrational numbers. I'll prove the log of 2 base 10 is irrational. If it was rational, then we could write 2 as 10 to the p over q, where p and q have no common factors. So that's the same as 2 to the q is 10 to the p, or 2 to the q minus p is 5 to the p, and with a little bit of work you can show that there's no way to do this. Q and p can't be the same, so we're going to have some power of 2, and that just can't happen, because this will be even and that will be odd. All right, so I took the square root of pi as one of my favorite numbers, and I looked at the fractional parts of n root pi mod 1, and I looked at the first 10 values, and I saw how many of them were between 0 and 0.1, how many were between 0.1 and 0.2, etc. The square root of pi is irrational. Does this data look reasonable to you? You're shaking your head. What's wrong with this data?
Why would so many values be 0.7?
What does this mean for how many values do I have in this bin? 2. I have 10 data points and I have 10 bins. How many points do you expect in each bin? 1. So this means this bin has one extra and this bin has one fewer. Now, if they were this pronounced when I had 10,000 data points, I would agree with you that I should be suspicious. I would actually claim that if every bin had one data point, I'd be suspicious the other way, that I cherry-picked the number. That there should be some fluctuations, but as I take larger and larger values of n, it should get less and less. And so here's n equals 100, n equals 1,000. And if you have really good eyes, you can see the fluctuations at n equals 10,000. All right, so the fundamental equivalence is a set of data is Benford if and only if its logarithm mod 1 is equidistributed. So this is the classic way of proving Benfordness. So here's the proof. I'll write my number as a significand times 10 to the k. When I take the log mod 1, this part vanishes. And so all that I really get is the log of the significand. I guess there should be parentheses around that. All right. So you're just plotting things. If I want to have a first digit of 1, I want to live between 1 and 2. So here's my numbers going from 1 to x, and then on the log scale going from 0 to 1. Which numbers on the log scale will exponentiate to a first digit of 1? Everything from 0 to the log of 2 base 10. Which numbers will have a first digit of 2? Everything from the log of 2 base 10 to the log of 3 base 10. And that's where you'll get the log of 3 halves, the log of 4 thirds. If it's easier to view it vertically, we can view it vertically. And we can say, well, if I want to have a first digit of d, let's say d is 5, I look at the probability I am at most here, which is the log of 5 base 10, and then I subtract off the log of, I subtract off the log of 6 base 10, I take the log of 6 base 10, I subtract off the log of 5 base 10, and that will give me all the numbers in here. And you can see when you sum it, we'll sum all the way up to 1. Here are our probabilities. All right. So 2 to the n is Benford, because the log of 2 base 10 is irrational. So Fibonacci numbers are Benford. And if you look at the recurrence relation, how many of you have never seen Benet's formula? Has everyone seen Benet's formula for Fibonacci's? How to solve recurrence relations? If you haven't seen it, you have to let me know. So I can guess an is r to the n. And if I guess that and I feed this in, I'll get r to the n plus 1 is r to the n plus r to the n minus 1. So I get r squared is r plus 1. So I get 2 possible roots for r. And then it turns out that you have linearity. If you have a solution, you can multiply the solution by a constant and it's still a solution. And you can add 2 solutions. This is also a very reasonable thing to expect. If I look at a to the n plus 1 is a to the n plus a to the n minus 1. So I'll do like this. A to the n plus 1 equals a to the n plus a to the n minus 1. I'll do the upper bound. Do we agree that a to the n plus 1 is less than or equal to twice an? Because the sequence is growing. And this immediately implies basically that a to the n is growing no faster than 2 to the n. If you go in the other direction, you'll get 2a n minus 1 is less than or equal to a n plus 1. So basically, every time you increase n by 2, you increase by at least a factor of 2. So basically, each time you increase n by 1, that's essentially like a square root of 2. And this will imply a of n is greater than or equal to square root of 2 to the n. So this is a very simple argument, and it tells us it's going faster than root 2 to the n, and it's going slower than 2 to the n. So it suggests that there really is a good reason to believe that the growth rate is like r to the n. And we get Benet's formula. When you plug in and look at the cases when n equals 1 and 2, you get this beautiful formula. So what I love about this is imagine that a crime has been committed, and the police form a lineup. And they get all the numbers that are suspected of doing the crime. Right? And they bring in the witness. to identify. And the witness is badly damaged from the incident, but they remember something very important. It was an integer that did this to me. Right? The Fibonacci numbers are integers. When you look at this, does this look like an integer? Not even close. You've got square roots, you've got divisions, but this will always be an integer. As a nice exercise, you can ask, what can you replace the 2 and the 5 with and have this always still be an integer? This is larger than 1 in absolute value, so as n gets very, very large, this is going to grow exponentially. This number is less than 1 in absolute value, so when n is huge, this is essentially meaningless. And so you can essentially just drop this part over here. The nth Fibonacci number is approximately just this. You need to do a little bookkeeping, but that's where the Benfordness is coming from. A multiplicative constant's not going to change things. It's really like the golden mean to the n. Most linear recurrence relations are Benford. So here's our, doubling. That's Benford. From the log of 2 base 10 is irrational. This one is not Benford. And the reason is if you try to solve it, the recurrence relation generates a characteristic polynomial, and the roots of that are a double root of 1. And 1 to the n has different behavior. So if you take a0 equals a1 equals 1, you get every term in the sequence is 1. So it's 1, 1, 1, 1, 1, 1, 1. If you take a0 equals 0 and a1 equals 1, you get 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are some cases that will not be Benford, but most cases will be Benford. Let's go back to powers of 2. So I've tried to list a couple of powers of 2. The numbers grow fast. They grow exponentially fast. So I can't really show too many. So I'm looking at data for the first 60, but I'm only going to display 30 just in the interest of space. Does it look like a good fit or a bad fit to Benford? I think it looks pretty good. What do you think is the most concerning number? Most concerning digit?
8.
8? Why 8?
Because we would expect it to be between 7 and 9, but instead it's much larger than both.
But this is the predicted value, 0.051, and it's actually 0.083.
Yeah.
So I actually don't think that's the worst. Because I'm looking at what I observe to what I predict.
Professor,
yes.
I think he meant that in a different
frame,
like comparing the 0.083 to
the one immediately
and the
above.
one below it.
Yeah, but I'm saying I do agree that it's a little strange that it jumps up there, but I think that it's not as bad as something else, because if you look at its size relative to this, it's not so bad relative to that versus something else.
Like 9.
Yeah, the 9 looks much worse to me, the 0.017 versus the 0.046. This is closer to like a factor of 3 difference, where this is less than a factor of 2 difference. Are you troubled by this?
Or maybe it's caused by small size.
Yeah, so we've had enough discussions about this over the day that it's small data, it's only 60. Right? How many people here are comfortable with computer science? How many megabytes are there in a gigabyte? 2 to the 10. 1,024. Not 1,000. If you use the correct Latin or Greek, it would be a factor of 1,000 difference. Why is it we use 1,024? Why does a gigabyte have 1,024 megabytes? Is it just that computer scientists, while they're really skilled at system architecture, just don't understand the classic languages? And we're now stuck with their mistake? What base do computers love? Base 2. So 2 to the 10 is so close to 1,000, yeah, just call it a mega to giga. And so I think this was the worst of the cases, but 2 to the 10 is almost 10 cubed. So imagine the world where the computer scientists are in some sense correct, and the ancient classic scholars are correct. And now 2 to the 10 is going to be exactly equal to 10 cubed. So imagine, this is not our world, okay? But imagine that 2 to the 10th actually equals 10 cubed. Then every time you increase by 10, you would just pad on 3 zeros. And if you notice, each row always has the same leading digit for each number. We haven't seen any 7s yet. And because we have an 8, we keep getting 8s, and that's where the 8s are coming from. Notice we don't see any 9s yet. Because we have an 8 early on, this is why in the beginning we're having so many 8s. As we go further and further and further, it will then start to converge to what we would expect. So, how many of you have seen chi-squared tests? So this is a concept in statistics. You want to see how close is your prediction to your observation. The smaller the number, the more likely it is that your conjectured behavior is correct. So I chose 3 numbers not at all at random. I chose the Euler-Mascheroni constant gamma, I chose the Euler constant E, and I chose pi. And for each one of them, I looked at the chi-squared values of, comparing the Benford probability to the observed probabilities. And the smaller the number, the better the fit. If it really is Benford, then most of the time, you should get a value of 15.5 or less. And then there's a great game or skit in Sesame Street called One of These Things Is Not Like the Other, One of These Things Just Doesn't Belong. When you look at this, which number looks like it has very different behavior? I'm sorry? Pi. I mean, pi starts off enormous, then it's getting down. Okay, so maybe it's a slower convergence rate. Then it shoots up. What's this? But then it starts to go down again. Are you convinced that the pi is going to go down to 0? A lot of mathematics is about how you present data. So I'm going to just look at pi to the n and e to the n, and I'm going to plot not the chi-squared values, but the log of the chi-squared values. And the reason is, if I don't plot with a logarithm, I've got a 46.65, and I've got a 0.06, and I've actually got a 0.03. To get them on the same scale is going to be very hard to see anything. But if I plot them on a log scale, it's a little bit better. So the blue is the log of the chi-squared values for e to the n, and the red is the log of the chi-squared values for pi to the n. What do you observe about the red plot? What do you see?
It's somewhat periodic.
It's somewhat periodic. Now, if it was periodic, they would have to go up to the same height. Do you think this is roughly the same shape as that one, is roughly the same shape as that one? Anybody want to guess the period? Rough guess. 180. Okay, now there's got to be at least one math geek or somebody who can act as a math geek. Can you rattle off digits of pi for me? Somebody's got to know a bunch of digits of pi.
3.1415.
926.
All right, good. All right, excellent. All right, that's the first order geek. Second order geek, who can give me digits of pi squared? 9. Okay, so nobody's really learned digits of pi squared. Pi cubed. If you calculate pi to the 175, you get 1.0028 times 10 to the 87. This is almost padding 87 zeros. Now, what was your guess for the period?
180.
If you look a little bit more closely, here's 100, 150, here's 200. Does that look like it's halfway between 150 and 200? I mean, your 180 is saying pretty much yes. That's what's going on. It's almost the same as padding 87 zeros, but it's not quite. It's similar to that 2 to the n is not quite 1,000. 2 to the 10 is not quite 1,000. and that as you keep going on, it will slowly start kicking in, and this is going to slowly be decreasing, but it will take a while. It'll take longer than it will take for 2 to the n. All right, so why is Benford's law true? So imagine you have a long street, and the houses have just integer values 1, 2, 3, 4, 5, all the way up to n. Well, if the street ends at house 199, or the street ends with 999, it's going to be very different. In the first case, you have almost 5/9 of the houses have a first digit of 1, and in the second it's only about 1/9. So it's going to really oscillate. And so if you plot it like this, what's the probability of a first digit as a function of the street length? Right? Instead of plotting the length of the street, if you plot the log of the length, now you see a nice periodic graph, basically. What we can do is we can start playing games with what if we had a bunch of streets of different lengths. So here, I'm going to assume we have streets. We have 1,000 streets, and each street is from 1 to 1,000. And I'm going to look at the first digit and the first 2 digits. And this is the Benford predictions, and this is what we observe. And you can see it's not even close to Benford. But now, I'm going to do 1,000 streets, and each street, I'm going to choose a random number from 1 to 10,000, and that will be the length of the street. So the street length is now going to be a random variable. And if you look at this now, does it look like it's Benford? No, but it looks closer. Now, I will choose a random number from 1 to 10,000, and then I'll choose a random number from 1 to whatever that was, and that will be my street length. So I'll double the process. Now it's not so far off from Benford. And if you do random, 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 it's now pretty close to Benford. So this is a general phenomenon. The more randomness you have, the more amalgamation you have, typically the closer to Benford you get. We've all done probability before, non-negative functions. Area under the curve is 1. The area between A and B is going to be the probability you take on a value between A and B. The mean is the average value. The variance is how spread out you are. Two things independent if knowledge of one gives you no information of knowledge of the other. Big result is the central limit theorem that says if you have a bunch of independent, identically distributed random variables, then the sum, the distribution of the sum, converges to a normal. Let me see if I can fix the recording. That does not look better. Now it does. Okay. So here is a uniform random variable, and I've chosen the region for the uniform random variable to be such that it has a variance of 1. That's the solid blue line, and that's the Gaussian. Do you think the Gaussian does a good job of modeling the sum of one random variable? No. It's not horrible, but it's not great. Do you know what the shape would be for the sum of 2 uniform random variables? If you've played any dice games, you should know this. If you roll 2 die, you have 6 out of 36 ways of getting a 7 for the sum, going all the way down to just 1 out of 36 ways of getting a 2 or a 12. You get a nice triangle. So here, does the Gaussian do a pretty good job for the sum of 2? It's actually not bad. The sum of 4 random variables, and it's easier to do things in powers of 2 with grouping and whatnot. The sum of 8. So you can see how quickly the convergence is settling in. Here is the explicit formula for the density for the sum of 4 uniform random variables. You can write it down. You don't want to see the formula for the sum of 8. You do not want to work with this. And this is why we love things like the central limit theorem. That's close enough. Let's just call it a Gaussian and move on. Okay? So here, let's look at what happens with a Gaussian if we look at the Gaussian mod 1. Okay, so here I claim that as n goes to infinity, if you look at a Gaussian with variance sigma, as the variance gets very, very, very large, if you then collapse it and look at it modulo 1, it's going to look like a uniform distribution. So here's the Gaussian with mean 0, variance sigma squared, and sigma squared is going to be 0.01. So that means the standard deviation is 1/10. So the most common value is going to be 0. And if you're 2 standard deviations away is going to be 0.2 in this direction, or going in the other direction to about 0.8. And you can see, yeah, most of the mass of the Gaussian is lying very close to the 0. Now let's increase the variance to 0.1. It's closer to the uniform. Let's increase it a little bit more. Oh, yeah, it's no longer so good. What went wrong? Yeah, look at the scales. Right? Over here, the scale goes from 1.2 down to 0. Always look at the label on the axes. Here it's going from 1.0001 to 0.9999. So yes, if you look at it like this, it looks like there's some great variation, but it's essentially constant. So already when the variance is a half, the Gaussian modulo 1 is very close to a uniform distribution. And so I've mentioned if you see a product, take a logarithm. Let's say you have a bunch of nice random variables and you want to look at their product. Maybe you have like length, width, and height of a bar of gold times the current price of gold on the market. And you want to try to calculate how much it's worth. Well, if we take the log of a product is the sum of the logs. By the central limit theorem, if these variables are nice and they don't have to be identically distributed, this should converge to becoming a Gaussian. But when we take for Benford's law, something is Benford if the log is equidistributed mod 1. So this is converging to a Gaussian with growing variance. We look at it modulo 1. When we look at it modulo 1, this is converging to uniform. That's the equidistribution. And this is just to give you some sense of why we have Benford in so many places. It's a central limit theorem kicking in. What's really going on is you're looking at things the wrong way. If you were to take the logarithm of the numbers and throw away the integer parts, you wouldn't see a digit bias. You'd also be shot for looking at numbers that way. If somebody asks you what's the temperature, they don't want you to take the logarithm and then throw away the integer part. They want a nice number that actually represents the physical quantity they care about. Applications. A tale of 2 Steve Millers. I assume you can figure out who one of the 2 Steve Millers is. I will talk about the other one in greater detail when the camera is not rolling. He used to be very high up in the Internal Revenue Service. He lost his job in the scandal when it was discovered that the IRS was declining or giving trouble to certain groups based on the political orientation of the groups. And in fact, it was so bad that some groups that were declined, they then reapplied, but they changed their names from one side of the political spectrum to the other side, and then got approved very quickly. And it's not good to be using politics to decide which things can go forward. You should be using mathematics. I will skip the tax returns of certain people. You can look at them later if you want. So a bank was audited, and they looked at how many numbers in their databases, certain fundamental numbers, started with the first digit of 1, of 2, of 3, and they compared that to Benford. And they saw that one of these numbers was a little bit higher than expected. Anybody know which digit?
8.
No. Try again. You're off by a factor of 2. What was that? 4. So there were a lot of numbers, a lot more than expected, that started with 4. So they investigated. And they saw that a lot of these numbers that started with 4, their second digit was high. There were a lot of 48s and 49s. And they traced it, a lot of it, to one person. Do you have a credit card?
I have a debit card.
Okay, that's close enough. Okay. So Joshua's the TA. Thank you. What should Joshua do really fast? Cancel his credit card, right? Or physically assault me, get you to help me. I'm glad that you chose the cancel the credit card rather than assaulting me.
This is the same card, right?
Yes.
Okay.
I actually sometimes do keep extra credit cards on me. I actually do have 2 other credit cards that I had loose, that if yours was either one of those colors, I was going to try to switch it on you.
Okay.
Imagine you have a credit card and it's stolen and you call up the bank. And are you liable for the charges? No. Now you're the bank and this credit card's been reported stolen and you see that there's your $13.12 in disputed charges. Do you assign an agent to find out who stole the card and track down the purchases? Or do you just pay the $13.12?
You'll probably pay.
You just pay it. It's not worth the time to track down the person for $13. This is like Bill Gates and 1,000. It's just not worth the time. Imagine it's $35,000 in charges. Did you track down the person now?
Yeah.
Yeah. So the way they did this is they had a ceiling. Anything below the ceiling would not be investigated. Anybody want to guess what the ceiling was?
Something starting with a 5.
Yeah, it was $5,000. So anything below $5,000, the person on the phone could, oh, I'm so sorry to hear your card was stolen. We're canceling the card right now. You're not liable to any of the charges. And they could just write off the expenses without an internal investigation. Anything below $5,000, they could do that for. Anything above $5,000, the bank had to investigate. And they noticed, there's a lot of 4849s coming from this one person. They were getting their friends to get credit cards, run up debts just below the 5,000 window, and call up and make sure they got him. If it wasn't, I just wanted a statement balance. Oh, I'm so sorry to hear your card was stolen. What should the credit card company do instead? Should we audit everybody? Or should we have an investigation for everything that's claimed to be lost? What do? Finite resources. Maybe anything over $10,000 you always investigate. Maybe anything $7,000 to $10,000 you investigate 95% of the time. $5,000 to $7,000 you investigate maybe 92% of the time. Then maybe $4,000 to $5,000 maybe you investigate 80% of the time. If you see an elderly grandmother with 2 adorable little kids boarding a plane, do you think you should randomly pull over grandma for extra security? Yes or no? Never? Really? So you're telling me now there is a category that will not be investigated, ever. Do you want to stick with your answer? Would you like to change it? Should you never investigate elderly grandmothers traveling with 2 little kids? Do you want to say to the world, this is a category that will not be investigated? Now, if there's somebody who is wearing, a Death to America shirt, say, or a shirt that says, I love blowing up planes, I'm just trying to make it very obvious here. Should that person be in the higher category to get special treatment? So the real question is, when you have finite resources, how do you want to allocate them? This is a real interesting problem in the real world. If there is a category that you never investigate, you now have a security hole. Right. And so as I said, it was the write-off of $5,000. So this is some stuff on streamflow data. I'll skip this. I'll skip the stuff on this. So here's one of my favorite examples. Who knows what steganography is? Excellent. People like the picture of the nice trees? Can people see the cat in the trees? No one sees the cat? Do you want me to show you where the cat is? Cat's everywhere. How do you transmit pictures? You often send a red, green, blue triple for each pixel, right? How much red, how much green, how much blue? Typically, you take them from 0 to 255. Why from 0 to 255?
That's 2 to the 8.
Yeah, it's 2 to the 8. So we're talking about bits, 0 or 1. So what you frequently can do is look at the last 2 bits, which will be 0, 0, 0, 1, 1, 0, and 1, 1. And let's say no matter what the last 2 bits are in your image, you will pull those out, and we'll take our cat, and we'll do the cat maybe in a very low res picture where the only values for the red, green, blue triples are we can basically do things at 0 fourths, 1 fourth, 2 fourths, or 3 fourths, or something like that. And then we'll just scale that down to be from 0, 0, 0, 1, 1, 0, 1, 1. And what you can then do is you can take the image of the cat and you can change just the last 2 bits of your image and hide the cat there. Instead of hiding the cat, you could actually take a text message. A text message is wonderful. You've only got black and white, so you're only changing 1 bit. And so the question is, how do you know that an image hasn't been modified? Maybe a terrorist has posted an image on the web with a message of instructions. Trust me, there are agencies around the world that are listening to emails and conversations and trying to look at patterns of communication. Can you send a secure signal? How can you tell if an image has been modified? And so one of the nice applications of Benford's law is to stuff like this. Can you tell if an image has been modified? So we've talked about the zeta function before, so I'm not going to go into too much detail. The zeta function, we've seen all this stuff. We have talked about how it has lots of applications. And I looked at values of the Riemann zeta function on the critical line, and I plotted it with Benford's law. And I can't remember if the diamond or the star is Benford, and the other one is the values of the L function, because I don't really need to. The fit is that good. It's incredible how many different systems Benford's law plays in. I'm not going to talk about generalizations and other L functions. I'll skip about that. I'll go to 3x plus 1. How many people here have heard of the 3x plus 1 problem? Okay. My 2 favorite quotes about this was, one is attributed to Kakatani. I think that this is a Soviet conspiracy to slow down American mathematics. He would travel, and when he was visiting colleagues, he would describe the problem. Well, that's not so bad. And then they give up in a month in frustration. And the other is due to Paul Erdős, who said mathematics is not yet ready for problems like this. So we'll define a map as follows. You give me an integer. If it's odd, I multiply by 3 and add 1. If it's even, I divide by 2. Lather, rinse, repeat. Okay? So 7 is odd. Goes to 22, 11, just keep iterating like this. And now what happens now that I'm at 1?
You're going to periodic time.
Yeah, so 1 will go to 4, 2, 1, and I'll just keep looping. So the conjecture is no matter what number you start with, you will always get into this 4, 2, 1 loop. And so I've given you the quotes. Here is looking at digits, looking at the observed probabilities and the Benford probabilities. And so Alex Kontorovich and I were able to prove Benfordness in some sense, and then Soundavarajan and Jeff Ligarius, another pair of people from Michigan, were able to prove Benfordness in an even better way. So lots of different things you can be doing here. I'm going to, I think, skip the conclusions and the references, and I'm going to end with the stick decomposition problem. Okay. Consider a stick of length L. Right? And then what we're going to do is we're going to fix a proportion in 0, 1 that will be fixed for all eternity. And we're going to break this stick into 2 smaller sticks at p% of the way down. And so we get a stick of length PL and another stick of length 1 minus PL. And then we take each of these sticks and we break them proportionally the same way. And we keep iterating. And we keep doing this, and we do this n times. Do you think that this will always, if you look at the distribution of lengths of the stick fragments, do you think that will always converge to Benford? Or do you think there are some probabilities that might cause trouble?
Yeah.
Okay. Which probabilities would cause trouble?
So you take my 0.1.
Yeah, if you take P to be either 0 or 1, you're not breaking it.
Like say you take 0.1, would you still get?
Well, if you do 0.1, you would then get 0.1 and 0.9 for the first one. then you get 0.01, I think 0.09 for the next one. So you'd start to get lots of different possibilities. There is one probability that should, your spider sense should tingle that this is a bad choice.
0.5.
Yeah, 0.5, because if you take 0.5, then you're splitting everything in half. So at stage n, everything has the same length. So maybe as long as you stay away from 0, 1, and a half, you'll be okay. And you can see, here's what's going on at step 2. As long as p is not a half, we'll have something of length p squared. We'll have two things of length p, 1 minus p, and we'll have one thing of length 1 minus p squared. And the further down you go, the more possibilities you have. And so here I took p equals 0.51, and you can see a really good fit with Benford. However, if you take p equals 1/11th, it's a very bad fit. And let's look at what's going on. So if you look at the stick lengths, the lengths are p to the k, and then 1 minus p to the n minus k. Right? That's the possible lengths you can have. What I can do, I just want to make sure I do it the same way over here, is I can pull out a p to the n. And so I now have p to the n times 1 minus p divided by p to the k power. So I can write this as p. I need an extra factor of n minus k. Or do I have it? Is it upside down?
No.
Oh, maybe I want to write it this way as n minus k and k here, just to match things. Okay, and then if I pull out a p to the n, I'll have the p to the k downstairs, and I'll have a 1 minus p to the k upstairs. So that's welcome. So that's the way so you're at the tail end of the Benford talk. So if I do it like this, I can see this factor is the same for everything in the level n, and then this factor is going to change depending on what k is. If 1 minus p over p is 10 to a rational number, then I'm only going to get finitely many possibilities. Notice that this looks a lot like our equidistribution stuff. If beta is irrational, then n beta mod 1 is equidistributed. Or more generally, if I have like a log base 10, so when I'm looking at what's going on here, if this is either a power of 10 or a rational power of 10, then every time j increases by a fixed amount, I'm going to just cycle back. And so I need to make sure that this stays away from being a power of 10. And so as long as you stay away from that, it's going to be Benford. And so here's what's going on with p equals 3/11ths. And you can see the log base 10 of 8/3 is irrational. It's not a bad fit to Benford. If I take 1/11th, this should look very non-Benford. Right? Where basically everything has that one common value. The proof of this is actually not that bad. And so there's a lot of different things you can look at on Benford's law. This is meant to give you some sense of the types of problems you can look at, some sense of the tools that will come into play. So there will be a lot of elementary Fourier analysis. You're not going to need the deep theorems such as, well, if I have a function that's L2 and I want to talk about convergence of the Fourier series, no, we're not going to need any of the stuff like that. Right. Any questions on Benfordness? All right, everybody's good on the Benfordness stuff? All right, I'm going to stop the recording.